Why is my Python code so slow? Guys, if you've been following along with my videos, you know that we wrote some code in our previous videos that was really good, but really slow. What's the problem with our code? We're using Python, and Python is slow. Just kidding. So you're going to hear this myth a lot, guys. Python is slow. Blame all of your problems on Python. Why don't you code with a real language like C++ or Rust? Well, I'm going to show you just how powerful Python can be when used properly, and that if your code is slow, it's not because Python is slow, it's probably because you're slow. But don't worry, we're going to fix that together. So let's get started. I've created this little code here to calculate Fibonacci numbers. Now, if you don't know what a Fibonacci number is, don't worry. It's a series of numbers. It's 0, 1, 1, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and you keep adding them together, and you get this really long list of numbers. It's a very basic math problem. You've probably heard of it. Anyways, I wrote code in Rust and Python, and we're going to explore that. And let's see how fast my Rust code can run. So my Rust code is right here. Rust's syntax can be quite similar to Python, so you can probably understand exactly what's happening. We're basically going to calculate the nth Fibonacci number, and to do that we're going to get the previous number and then the previous number, add them together, right? That's the sequence. So we're going to use Rust to do this. Now, if you're not familiar with Rust, Rust is a compiled language, and it's very fast, allegedly. It's fast on par with C is the claim, which is probably true. It's probably 100 to 200 times faster than Python, apples to apples, something like that. Doesn't matter. So let's look at the code. Let's run this. I'm going to calculate the 50th Fibonacci number. So in the sequence of numbers, I want to get the 50th one. Let's see how long it takes Rust to do that. So let me go into my Rust folder here, and I'm going to run this with a cargo command, cargo run, and then I'm going to do the -r flag. So just so you know, -r is a release flag. So the compiler is going to optimize this code for maximum speed. So I'm not cheating here. We're not doing like a debug version. So here we go. Okay, this is going to take a little while, guys. I'm going to cut the video ahead and I'll be right back. Okay, we got the 50th Fibonacci number. It's a very big number. You can see it down there. It took Rust 47 seconds to execute. 47 seconds. So let's see how quick my Python implementation can solve the exact same problem. So let me run python fib.py. Wow, almost instant. Almost instant. Look at how fast that was. Rust took 47 seconds to do the exact same thing and get the same number. And Rust is supposed to be 200, 300 times faster than Python. What's going on? Well, let's take a look. I actually wrote 3 versions of this software in Python, and this is to illustrate how very short, simple code, changes to our code, can have huge impacts on your performance. And with Python, we can get good performance, but it's up to you to get good performance. So there's 3 different implementations. Let's take a look at what each of these implementations are. We're not going to type all this stuff out. So in the first one, which I'm calling the bad method, we are calculating the Fibonacci number using a recursive formula, because the Fibonacci is inherently a recursive formula. It's the current number is the previous number plus the previous number. So the problem with this is that this creates an exponential growth of a tree. When we calculate the 10th Fibonacci number, we then have to calculate the 9th and the 8th. And when we calculate the 9th number, that's going to be part of that 10th number, that breaks down into the 8th and the 7th. So now I'm calculating the 8th over here, and I got to calculate it again over here. Then I break that 8th down, and I have 7 and 6. And the bigger our n gets, if we go up to n100, it's basically a tree, and it opens up exponentially. It gets exponentially slower. And that's how we implemented our Rust code. We used a recursive formula, and Rust exponentially got slower. So how can we make this better? So did I use any magical tools with Python? Did we do anything special? No, I only used built-in Python code. So the only imports I have here are time and matplotlib, because we're going to plot this and show how this looks. So a better way to implement this to prevent a tree from just opening up and exponentially slowing down our code, exponentially becoming more costly. What if we calculate each number just once? So we don't recursively calculate it. First we calculate 0, then we calculate 1. So that's what's going on here. So if you want the first Fibonacci, it's always 0. The second Fibonacci is always 1. And then the third one, and anything bigger, it's going to be, let's add this one to this one. So instead of recursively doing this tree, now what I'm doing is I've created a list here, and I'm just making this list grow. So I'm adding a third one, and the third one should equal to the -1 and -2 index, so the previous two. Then I go again, add another one on, should be the last one and the second to last one. So instead I'm just adding the last two items in my list to the end of my list and appending it. And this makes sure that we only calculate every Fibonacci once. This takes our exponential formula and makes it linear. So here's what we're going to do. We're going to calculate up to, let's start with the maybe the 35th number. So this is going to loop over. It's going to start at 1, 2, 3, 4. And we're going to check the time it takes for Fibonacci formula number 1 and Fibonacci method number 2. We're going to plot the time it takes for those functions to execute. So let me run this code. Okay. Sorry, there's a little bug here. We can't start at index 0 because I have it coded where n starts at the first, second, third index of the series. So let me fix that. So we need to start at 1 to 35 instead of 0 to 35. Let me save that. Let's run our code here. And here we go. Okay, so we can see that when we went from the 0th up to the 35th, the Fibonacci 2 method basically took almost 0 time, all the way up to 35, while our Fibonacci 1 method, which is what Rust was programmed to do, exponentially got slower. And we can even make this more clear. Let's go all the way up. Let's try going up to 40. I might have to speed up the video because this might take a few minutes, guys. I will speed up the video. Let me run this. Oops. Okay. So when we got to the 40th one, before we were somewhere down here at 35, we were like at, half a second. When we get up to 40, now we're at 12 seconds of execution approximately. So can you imagine if I wanted the 5,000th Fibonacci number, how long this is going to take when it grows exponentially? It might take years or a decade or 100 years. It might be literally impossible even with the fastest computers using that method. However, my Fibonacci 2 is almost still 0 all the way up to 40, which means I might be able to push this thing up to 5,000 and it would still execute. So let's try that. Let's try that and see what we can do. So I'm going to comment out Fibonacci 1 here, guys, because if I don't, it's going to make this thing impossibly slow to use. Okay. So I've got Fibonacci 2, and I'm going to try, instead of doing this up to 40, let's do up to 5,000, which again, the other code, it might take a decade, 10 years to execute. Let's try this out. Let's see how this works. Okay, only took about 1 or 2 seconds. So after 2 seconds, we were able to calculate every Fibonacci number between 0 and 5,000. That's very impressive. And we did it from scratch each time. So we basically reset it and calculated it as if we had started again, clean. So we weren't just growing a single tree. This is actually starting over. Now you might be wondering, why does this thing look so spiky? Like it's only 0.0016 seconds versus Rust, which was 47 seconds, and that was only to get number 50. Here we're getting number 5,000 in native Python, and it's only taking us 0.0016 seconds. So that's awesome. But you're going to notice there's a lot of these huge spikes. So this is already really great. We already have what we call O of n runtime. We have a linear runtime. You can see this line here. Basically, it's a line with these spikes. Ignore the spikes. We basically have a linear line. So if this goes up 1,000 times, this time is only going to go up 1,000 times. And if this increases by 1,000 times, 1, 2, 3, that's only going to take 1.6 seconds. So I could calculate extremely large Fibonacci numbers in seconds versus the other method, which could take decades to calculate a number. But can we make this even better? Well, let's look at these spikes. What do you think is causing these spikes? You got any idea? It's probably the garbage collector, or it's the way we're allocating memory. So remember how I said there's probably even another way, a better way for us to execute our code? That's method number 3. So let's look at method number 3. So we've already improved where we're only calculating each number once. We're no longer exponentially slowing down our algorithm. So this is the bad method. This is a better method. But what we're doing here is we're taking this array and we keep appending to it. So this array is getting bigger and bigger and bigger. And what happens is Python is allocating a certain amount of memory. You fill that up with, let's say, 50 numbers, and then it has to add another 50 indexes of space. It has to allocate that, because you keep growing your array, and then it has to do it again and again. And every time it does that, it has to move memory around and stuff like that. So that actually slows our code down a little bit. This has a much smaller impact than number 1, but it still has an impact. So we can actually make this an even better solution. And how do we do that? Well, we do the exact same thing we did in number 2, except this time we don't have an array that we append to. We just have a fixed array. It could be either 3 variables stored in memory or a fixed array of 3 integers. And we are just going to store the current number. We're going to calculate the current number from the previous 2 right here. So Fibonacci number 2 is going to be the 0 in the first position, these 2 added together. We're going to put that number in there. Then we're going to basically slide everything over. So we're going to move 1 to 0. So 0 equals 1 now. So we're sliding the 1 over here. And then we're going to slide this new number that we just calculated over to the middle. Then we go through the loop again. Now we calculate a new one. So the difference is we're doing the exact same thing. We're calculating each Fibonacci number once, but we're only doing it in 3 spots in memory. We're not just making our memory grow and grow and grow. So let's take a look and see how this approach affects the result. Okay, so after running Fibonacci 2 and Fibonacci 3 together, you can see that we still have a similar issue where as our integers start to get bigger and bigger and bigger, we probably have to move memory around a little bit as those integers go from maybe 8-bit to 16-bit to 32-bit to 128-bit, because the numbers start getting really big. So you're still going to see those spikes even on the orange line, which is Fibonacci 3. But do you notice how Fibonacci 3 actually grows a little bit less than the blue one? That's because we don't have this giant array that we occasionally have to move around and readjust. Not a huge impact. When we get out to 5,000, we're only looking at 0.00007 versus 0.001. So it's very close. But the point is that those small optimizations, when your data starts to get huge, make an impact. But when we compare that with our Fibonacci 1, the impact is ginormous. It's ridiculous. You could never do this calculation. It would take a lifetime to calculate. So I wanted to share this video with you for 2 reasons. I want you to be sure that Python is not a slow language. There are just slow algorithms and slow methods. Now, is Rust a faster language than Python? Yes, it's about, let's say, 300 times, 200 times, 100 times faster. So what? I can calculate the 5,000th Fibonacci number in 0.001 seconds. Rust is going to do it in 100 times faster than that. You're not going to notice any difference. And for high performance applications in Python, we also have access to a lot of C libraries with things like NumPy. So we actually can access those low-level fast libraries when we need to. But even with Python's built-in libraries, the most important thing is that we have good data structures, good algorithms to get performance. So I wanted to share this with you so you could understand that, because it's going to be important as we go into our projects that we've been working on. We have to speed up our projects. Our Lego brick calculation and our video processing is too slow right now, and we're going to have to do some digging to improve our algorithms and our methods to speed it up. So I hope you found this video interesting. Remember, Python is not slow. You're slow. Enjoy the rest of your day, and I'll see you in the next video. Bye.